Heat Power, Chapter 2. Let's talk about pure substances. What is a pure substance? Is a pure substance like water when you go to the mountains and the stream is flowing down and you drink some water and it's pure water? That's not what we mean by pure substances. We're going to change your vocabulary just a little bit. A pure substance is a substance that has a fixed and uniform chemical composition. So the chemical composition is not changing, and it's the same throughout. If you have a glass of water, let's say you go to a pond, okay, and you get a glass of pond water, it's got mud in it, okay, is that a pure substance? Well, as long as the mud particles remain suspended in that water and uniform throughout, therefore, yes, it's a pure substance. Now that doesn't mean you'd want to drink it, okay? All that means is that it is a substance that has a fixed, not reacting, not changing, and uniform, same throughout, chemical composition. So let's take some examples and decide whether or not they are pure substances. Let's start with nitrogen. Say we had a bottle of nitrogen, okay, maybe for welding or some purpose. Is the nitrogen a pure substance? Well, the nitrogen's not reacting, it's just remaining as a molecule in2. It's pressurized. Even if we let some of it out, it very quickly is the same even concentration throughout, right? It's the same density everywhere. And its chemical composition is not changing, it's uniform, so yes, that is a pure substance. What about air? Well, you might look at air and think, well, I know that air consists of nitrogen and oxygen, so surely it's not pure because there's two different chemical species in it. Well, as long as the relative amounts of nitrogen and oxygen remain the same, then yes, air is a pure substance because it is a fixed and uniform chemical composition. It's not like the oxygen goes over to that side of the container and the nitrogen goes to the other. If that happened, then it would not be. Let's talk about water. Now here's a tricky one. What about just water? Say we had nothing but H2O in a container, but some of it was in the vapor phase and some of it was liquid. Then would it be fixed? Well, remember, we're not talking about a uniform phase distribution. We're talking about a uniform chemical composition instead. And the vapor is all pure water, assuming we have no air in this container. And the liquid is all pure water. So yes, actually, this is a pure substance. Now let's take that same consideration to air. What if we take air and we cool it down to the point where it begins to liquefy? Well, if you know anything about air, of course you know it's primarily nitrogen and oxygen. I don't remember which, but one of those actually starts condensing out first. One has a higher boiling point and the other one has a lower boiling point. So the one with a higher boiling point will start to condense out first, and so the liquid will be rich in that component. So there will be a different chemical composition in the vapor, which will likely have some nitrogen and oxygen in it, and in the liquid. So that would not be, because it's not a uniform. Now it's fixed, it's not reacting and changing. I guess you could say that it's not really fixed because the liquid is increasing, but so that there's a change in the chemical composition of the vapor. But well, really that would be the reason, right? That things are changing, and so the composition is not fixed. And of course it's not a uniform composition, right? There's the vapor is rich in one of the two and the liquid is rich in the other. So that is not an example of a pure substance. Speaking of phases, there are three primary phases. There's solid, liquid, and gas. Of course there's also plasma, but we're not interested in that. We're not going to do anything with plasma in this class. And there are some interesting distinctions between them. For example, if you try to run your hand through air, it's no problem, right? That's easy. You try to run your hand through a bath of water, sure, no problem, right? But if you try to run your hand through ice, now you'll have a problem, right? Because it's a solid, and the bond strength of the molecules to each other in a solid ice, for example, is much, much stronger than the bond strength between the molecules that make up liquid. And so you can't run your hand through it. Now, a gas, if you just have vapor, water vapor, running your hand through it is pretty easy, right? Easier even than running your hand through liquid. So we say that the bond strength is strong in solids, medium in liquids, and weak in gases. Energy, on the other hand, is low. Think about ice. If you have ice, how do you make vapor or steam from that ice? Well, you have to add energy into it, don't you? And so the amount of energy in the solid ice is less than the amount of energy in the liquid, which is even less than the amount of energy in the vapor, right? So in that order, we go from low to medium to high energy in the phases. How about order? Well, the order or the crystalline structure is much more organized, right, in solids than in liquids, and liquids are more organized than gases, and so the order changes as well. How orderly these things are changes. Now, what is a phase? How do we identify a distinction? How do we make a differentiation between the various phases? Well, one way is by the distinct molecular arrangement. Now, a lot of times you can't see that, right? You have to somehow infer it. But a distinct molecular arrangement, for example, if you think of carbon, carbon has two very specific solid phases that you may be familiar with. One is called graphite, and the other one's called diamond. One is in your pencil, and the other one is really expensive, right? You may not even have any of it because it's so expensive, yet it's still all carbon, right? So one of these phases, if you try to put the wrong phase on the ring and ask your partner for their hand in marriage, they're going to say no, right? You got to get the phase right. Now, another way to identify phases is that the phase itself is homogeneous. It's the same throughout. Okay. Also, how do you detect various phases? Well, there can be boundaries that are recognized. For example, if you think of an ice bath, ice and water together, there's a distinct boundary between the solid water and the liquid water, and that differentiates the two phases from one another.